Okay, we have a sample problem. A dense silt layer has the following properties. We are given with void ratio, effective diameter, capillary constant, and free ground level, which is 8 meters below the ground surface. You're going to A, find the height of capillary rise. Capillary rise given as C all over E times D sub 10. Then find the vertical effective stress in kilopascal at 5 meters depth. Assume unit weight of solid is equal to 26.5 kilonewton per cubic meter, and that the soil above the capillary action rise and the ground surface is partially saturated at 50%. Letter C, find the vertical effective stress at 10 meters depth. Assume unit weight of the solid is 26.5 kilonewton per cubic meter and the soil above the capillary action rise and the ground surface is partially saturated at 50%. So for this problem, we're trying to solve first for the capillary rise. This is the equation for capillary rise. We're given with our C, our D sub 10. So we simply have 2 and we have given with our E. So substitute the given value for the parameters. Our H, which is the height of the capillary rise, is 5 meters. So we have here the figure for our problem. So actually we're just given with the unit weight of the solid, which is 26.5. So we try to compute first for the saturated unit weight and the unit weight of the soil within this layer, the unsaturated layer. So since we are given with the unit weight of the solid, so we can compute for our unit weight of the unsaturated soil and the saturated soil. So we try to get first our specific gravity. So from this equation, unit weight of the solid equal to the unit weight of the water times G. Simply have to substitute the given parameters. Our G now is specific gravity is equal to 2.7. So we try to get now the unit weight of the unsaturated soil. So unsaturated is this portion. So this is the unsaturated soil. So that is equal to this equation. So we have the specific gravity now. Degree of saturation, where E is void ratio, the unit weight of the water. Our degree of saturation is given by, for this one, it is partially saturated at 50%. So basically that is 0.5 or 50%, which is our degree of saturation. So if we try to substitute the given values, our unsaturated unit weight is 20.33 kilonewton per cubic meter. And for our saturated unit weight, given by this equation, so simply have to substitute our specific gravity, void ratio, and the unit weight of the water. It gives us 21.73 kilonewton per cubic meter. Now we try now to get the effective stress at point A. So if we try to get the effective stress, we have to solve first for our total stress at point A. So the total stress at point A, this is point A, so that will be equal to 2 times our saturated unit weight, since this is within the capillary rise. So we need to say that is 21.73, this is the saturated unit weight, times 2, this height from the surface towards point A, then plus 3 times the unsaturated unit weight, which is 20.33, and it gives us 104.45 kilopascal. Then we try to get our pore water pressure. Since our point A is within the capillary rise. This is our capillary rise. So point A is within the capillary rise. So meaning to say our pore water pressure at point A will be equivalent to, that is negative 9.81 times 3. So basically this is point A. So we have 3, this one, 3 times 9.81. Since this is within the capillary rise point A, so this is pore water pressure is equal to negative 3 times 9.81. So it gives us the value of negative 29.43 kilopascal. Then we try to get our effective stress. So we simply have to substitute the value of the total stress and the pore water pressure. Our effective stress now is 133.88 kilopascal. And the last one is to compute for the vertical stress at point B. So the vertical stress at point B, this is our point B. What will be the vertical stress at point B? So we try to get, for the effective vertical stress at point B, we try to solve first for our total stress. For the total stress at point B, that will be equal to 2 times our saturated unit weight is 21.73, then plus 5, this layer is 5 times saturated unit weight 21.73, then plus 3 times unsaturated unit weight, which is 20.33. And the result here for the total stress is 213.1. The pore water pressure at point B will be equivalent to this, the water table. So the height of the water is 2. So we need to say the pore water pressure at point B is equal to 2 times the unit weight of the water, 9.81. So the result is 19.62. So therefore, the effective stress at point B is equal to subtract total stress minus our pore water pressure. So 213.1 minus 19.62. The result is 193.48 kilopascal. So this one is another way to solve for the effective vertical stress, but I think it is what I have discussed was the most convenient way to solve for the effective vertical stress, so that we will have a clear understanding. We try to get first our total stress, our pore water pressure, then after you have the result of our effect, total stress and effect and the pore water pressure, get the sum to get your effective, get the difference between the two rather, to get the effective stress at that certain point. So for this one, at point B, the effective stress is 193.48 kilopascal. So that ends our discussion for our in situ stresses in soil mass. So basically, our main concept here is total stress is equal to effective stress plus pore water pressure. However, we are after for the computation of the effective stress. So to get the effective stress equal to total stress minus pore water pressure, you simply have to get the value first based on our diagram, our figure, the value for the total stress and the pore water pressure. Get the difference between the two, you have now the value for the effective stress. So that ends our discussion for in situ stresses. So if you have questions, you may ask questions.